Alright, so today we're going to be doing day 22 in Advent of Code. The first part of the challenge is that we have some monkeys and they're trading and they have a market, and apparently what the buyers seem to do is that they buy using random prices, but they're not really random, they're pseudo-random. And what that means is that, okay, if we have a certain number, then let's say we multiply it by 10, we divide it by 5, by some set amount of multiplications and divisions and operations, and then we get a new number, which would be the pseudo-random number. So it's not truly random if you know what algorithm you're using to get the new number. And we know that their secret number, it evolves on a certain set of rules. And here are the rules. We calculate the result by multiplying the secret number by 64. Then we mix it, and they're going to define what mixing is later. And then we prune it as well, and they also define pruning later. After we divide the secret number by 32, we mix and prune it as well. Then we multiply by 2048 and we mix it and prune it again. What does mixing mean? It means that we do a bitwise XOR, which means exclusive OR operation. And pruning just means that we do modulus with this number from whatever number we initially had. So to do a bitwise XOR, if we have some numbers, so if we have two numbers, 0 and 0, bitwise XOR, in Python you can just make this upper arrow thing, and you do a bitwise XOR with two different numbers. So if you have two zeros, it will become a 0 because it only works if it's exclusively OR. So in the middle here we can see that either this or this one is a 1, so exclusively one of them is a 1, so then it returns 1. And exclusively one of them is a 1 here as well. But in the last case, both of them are 1, so it returns a 0. And the AND operator is a bit different. It's actually exactly the opposite. So if both of them are the same, then it returns a 1. Otherwise, it returns a 0. So that's how the XOR operator works, exclusive OR. And to just do pruning, we will just be doing modulus. So let's see the implementation. So I've implemented it in two different ways. But let's just talk about how we're doing this. So I'm going to be opening the input file, which we get from the website, and putting it in lines. And then what we do is we just iterate through all the lines, and we store whatever secret from whatever line we're reading as an integer into the secrets. That's what I'm doing. And what they want is not just the first iteration, so after one iteration of 1, 2, 3, after we plop it through this randomizer, so to say, then it becomes this number. Next time we do it, we get this number. But what they want is what happens after the 2000th time that we do this, that we iterate this. And not only what happens after the 2000th time, but for each different user or monkey that is giving us these random numbers, what is the added total of these 2000th secret numbers. So we take, for this number, we take the 2000th iteration of doing that, and then of the next one, and so on and so forth. So that is why we call this thing 2000 times, and the function secret step, it just does all of the different calculations from the input, and then it gives us an output, which we take, and then we do this 2000 times for each line in the lines, so for each number that we have, and then we add it to a total. And I've also timed them in the beginning and the end to see which one is faster, because I've done two different implementations, which I'll talk about. So first thing they wanted us to do was to multiply by 64. So I take the secret, I multiply by 64, and we just store it in temp, because what they want us to do is to do the XOR operator, and this is how you can do an XOR operation in Python, by just saying this character, and then we store it in secret again. Then they want us to prune it by this number, and we do modulus to prune it, and the modulus operator is just this. We store it back inside temp, that's what they tell us. Then they want us to calculate the same thing, but we do a floor division of 32, because they say that they want us to round down to the nearest integer. We store it in temp again, so that we can do a mix once again. And we do again modulus with this number, and then lastly we multiply by 2048, and then do a mix and a prune. So it's always do something and then mix, prune, do something, mix, prune, do something, mix, prune. Then at the end of all of these steps we can return the secret, so that is one total randomizing step And once we've done this 2,000 times, we add it to the total secret. So for each different line, we add it. And this is one way to do it. Another way to do it is if we realize that 64 is just a power of 2, so it's 2 to the power of 8, and 32 is 2 to the power of 7, and this number is actually 4096 times 4096, or to the power of 2. And since 4096 is also a power of 2, we can just write this as a power of 2. So when we do these operations, instead of multiplying or dividing, what we can do is we can just left shift or right shift, which would become the same thing. Because if we have the number 4, which if we write it, let's see, if we write it in bits, it would be, this is the ones place, this is the twos place, this is the fours place, and this is the eights place. So if we want to multiply by 4, what we would do is we would just see, okay, that 4 is equal to 2 to the power of 2. So we get it in base 2. So that means that we have to shift it to the left 2 times. So we have to shift this thing to the left 2 times. So then it would be 1, 0, 0, 0, 0. And then in this place, it would be the 16th place. And this would be the 8th place still. So if we do 4 times 4, then it is 16. So it is the same as left shifting. And it's a similar story when we right shift, because we don't actually care about the numbers that disappear when we right shift, because we're doing floor division anyways. So this is what I've implemented here. Shift step, it's not necessary, but it's just a different way to do it to see if it is more efficient or not. But sadly, I've tested it and it's actually not more efficient. So we left shift by 6 bits, or we right shift by 6 bits, or we left shift by 11 bits, and that's the 2048. And this thing here, that's why I've shown the example of the AND operator as well, because when we do, we can just do a AND operator instead of doing modulus with this number, and it's the same thing. And it says 0x because it's a hex representation of this number, since this number is 2 to the power of 24. And we can see that we can either store it as bits, so 24 zeros and ones, or we can store it as a hex value. And since the hex value is 0 through 15, so it's 0 through 9 and then 8 through F, then there's going to be 6 digits. So instead of 24 digits, it's 6 of them, because if we divide 24 by 6, we get 4, so it means it's storing 4 times as much information per digit as opposed to a base 2, and that is correct because it's storing up to 16, and that is 4 twos, 4 base 2 digits. Okay, and we are basically doing the exact same thing, pruning and mixing, and then we return the same number. And I've done 2 different loops here, the timer for the secret step and for the shift step. So it's the exact same code in both these steps here. And what we do later is we can just print both of them to see if they are the same, if I haven't made some mistake somewhere. And then we take the end time. So we always start a timer in the beginning, and then we end it once everything has ran through. And then we check the difference, and I say .6f to give me the last 6 digits after the decimal place. And what's going on? Shouldn't take this long. It says 12 and 8, and we can see that the numbers are pretty much the same. It's probably because I'm recording. It's a lot slower than usual, but I've run it several times before. Can we see any times that I have done it? Oh well. And the numbers are actually pretty much the same when we run one or the other. Yeah, so now it's 7 and 6.9, so it was just fluke luck that this one took a lot longer. But if we run it several times, we will see that both are actually the same. So that was part 1. Now if we go to part 2, what they want us to do is, okay, we have this really big number that we got that apparently is the price, but actually it's not the price. Only the last digit is the price, because who would pay this much for a banana? It's crazy. So once we do that, once we just keep the last digit, what we want to do is we will have different price sort of histories, and we can sort of predict what the prices will be because we know what the randomizer function is. and we want to get, okay, all of the different prices, so from one specific user or monkey, so this specific one with this initial price, we know what the next 2000 prices will be because we are doing this 2000 times. And then what we want to do is to store the difference in price between this one and the next one, this one and the next one, and so on and so forth. So these right here are just the differences between this 3 and this 0. It's -3. The price went down by 3. And then what we want to do is to give a monkey input, or a robot an input, to say, okay, whenever we see that a -3, a 6, a -1, and a -1 price change happens, we want directly after this to buy how many bananas are here. We're not actually buying it, we're just giving it some information, and then we're getting how many bananas it says here. And our goal is to get as many bananas as possible. So if we give it these 4 sequences, we're going to get 4 bananas. If we give it these 4 sequences, we're going to get 6 bananas, which is better. But not only are we doing this for a single monkey, we're doing this for all of the monkeys, and we have to see what is the best possible way, combination that we can give to get the most bananas. And we cannot change our combination. If we select that we want -3, 6, -1, and -1, we have to give that to every single monkey, and then whatever they give us is what they give us. If they haven't found that combination at all, then they won't give us any bananas at all. So we could either do this by sort of just going through all the numbers, so we know that we can go from, if I can just delete this, and okay, so we know that we can go from -9 to 9, so that is 19 different digits. But if we do 19 times 19 times 19 times 19, or 19 to the power of 4, that's going to be a really big number. And not only that, but we have to do that for 2000 times. So we have to multiply this by 2000 to get all of the price histories. And also we have to multiply by every monkey that there is. So let me just look at the input file and see how many there are. It seems like we have about 2200. So we have to also multiply by 2200. And if we multiply all of these numbers, it's not a division, it's just the summary, then we get the number that is in the billions. So it's going to be quite slow. So we can imagine that most combinations won't even happen actually. So we don't even need to sort of check them. We're just wasting a lot of time if we sort of brute force our way through this. So instead what we can do is we can store all of the combinations that happen. So we go through every single monkey and we say, okay, this combination we store it, this combination we store it. So every sequence of 4 combinations we store it. And then once we've done that through all of them, we see, okay, which ones of them give us the most bananas. And from that, we just see which one gave us the most bananas, and that's what we return. And we have some examples here. If we use these numbers, we would get 6 bananas in here, because 1, 2, 3, 4, and then we would get this banana if we use these numbers. So here's another sample. So if we have these initial numbers from the 4 different monkeys, what would happen, and they're sort of walking us through what's going on. But I'm going to walk you through, guys, through the actual code. So we have the secret step again, but we've cleaned it up to just make everything in one go. So we take the secret times 64, and then we do a bitwise OR with the original number which we had. Then we do a modulus with whatever number they told us to do, and then we put it back into secret. We do the same thing, but by dividing by 32 with floor division, and then times 2048, and then we return it. So this is just one step. And then basically what we do is I've made this find max bananas, and then it returns max bananas and the best sequence, just because why not? We only actually need to return the max bananas because that's the answer that they want us to give them. But if we look at this function, what we have is we take all of the lines and we iterate through every single line, and we only keep the last digit. So if we do modulus 10, what's going to happen is we're going to just keep the last digit, because everything that's bigger than 10 is not going to be a remainder. Everything that's smaller than 10 is going to be a remainder, meaning that we're just keeping the last digit, and that's what we want. So we keep the last digit, and then we generate the 2000 price steps, and we add it to the price list, which will be useful for later. Then we have some tracked sequences, and here is where we iterate through 5 consecutive prices. And why is it 5? Well, because we have to have the first 4, which is the sequence, and the 5th one, which is the actual price. And not only that, but we have to compare sort of the first 4. So if we have 4 of them here, and we have to compare them with these 4. So they will be offset by 1. And this one is the 5th one. So we have to get 5 of them at once to be able to compute the differences. So we compute the differences and we store it into price change. And we can see that we get the price list from the index to index plus 5 to get 5 different indexes. Then we put it in P1, P2, P3, P4, P5. And then we see the price change. And then if the price is already in the tracked sequences, it means that, okay, we have already passed a point where those price changes, so 4 specific price changes, they've already happened. So there's no point in adding what price that banana is at that point, because they mention in the problem that, okay, if a specific sequence has already happened, so if somehow here we have this sequence, -3, 6, -1, 1, if we have it again here, then we can't even get to it because we only get the amount of bananas from the first time the sequence happens. So in this case, we would be getting a 4. So there's no point in storing it again because we will never be using it. So that's why we just say continue here. But otherwise, we add it to the tracked sequences. And if the price is not in the sequence totals, then we say that it's 0. So we initialize it. And then we add whatever P5 is, so the 5th number. So the first 4 or the actual sequence, and then the 5th one is the actual number of bananas that we would be getting. And once we do this for every line in the lines, eventually we're going to get a lot of sequence totals, and we're going to find max of the sequence totals. And we can just use a normal Python function max, and we give it what we want to find the max in. And we're gonna say that the key is what we want to get the max of. But we've actually implemented the find max ourselves just to see how it works, and it's pretty simple. So the max key right now is nothing. The max value is -infinity, just because I can't just say 0. What if the max value is a negative number, like -10? Then it will say that 0 was actually the max. And what we do in here in this for loop is we take the key and the value, and we just see, okay, if the value is bigger than the max value, make the max value the value. And then we keep iterating, and we only keep the biggest number that we've seen. So every time we see a bigger number, that's the one that we keep. And that's how we can get the maximum key. And we return it from this function. But this is unnecessary. It's just to show how this actually works. And to get the max bananas, we can look in the sequence totals and then give it the best sequence. But it's not actually necessary. And in this function, we return both so that we can print both. So if we run it, it takes a couple seconds, and we will see what the actual max bananas is and what the best sequence was to give us that amount of bananas. And the answer, in my case, is not going to be the same for you, but in my case, with my input, it was 2121. So if it wants to finish running, we will see what the actual output was, but it should be correct. Seems it's going to take a while since I'm recording as well, so we can go through the time complexities of part 1. So in part 1, we have n as the number of lines in the input. So in our case, n is 2268, and it's probably going to be different for you. And the time complexity is going to be to read the input, the outer loop that we have over here, so each line, and then the inner loop, which is 2000. So the inner loop is 2000 times n, and this would just be n, because 2000 is a constant. So the time complexity is O of n in this case. And then the space complexity is the same O of n. And then if we look at part 2, the time complexity is actually exactly the same, because we also have a bunch more iterations, but since they're constant, then they count as n. And if, as we saw, part 2 did actually run slower, and this doesn't reflect on how fast the code is compared to a smaller file or a bigger file. It's just how much slower this one is compared to this one. So sure, it might be 5 times slower, but if we make the input file 10 times bigger then this one will be 10 times slower and this one will be 10 times slower, but also the comparison between them two will be the exact same as it was in the beginning. So the space and time complexity is also the same actually for part 1 and part 2. And we see that it actually finished running 2121, and that is the same answer that we got here. So if you guys want to join the leaderboard, I'll leave the code in the description, and thank you for watching, and happy holidays, and see you tomorrow.